I'm confused about the relationship between magnetic field and magnetic force, if you're able to explain that. Okay, so I got lots of ways we can talk about it. First of all, you'd want to think about it. I guess I should flip over here. Happy. So we're talking about the magnetic field, which I'm going to give the letter B. Okay. And then the magnetic force, we'd have to describe as FB, the force of the magnetic field on something. So this is magnetic field. Now, are we talking about a wire or are we talking about a charge?
Right, this guy or
this guy. Okay, just a charge. Okay. So when I'm talking about this in either my AP Physics 2 class or my Physics C class, what I'm thinking about is what's a magnetic field? What can make a magnetic field? So, it goes through that thing about magnetic domains, and you start talking about all the little pieces of electrons are working together or against each other. So if you can do that. So this is that's your first introduction to the generation of a magnetic field is caused by moving charges. Okay. So when you have these moving charges generate magnetic fields. Now, from a very early age, you got to explore magnets and play with them. You stick stuff to one of your 9 refrigerators. You get to experience that right off the bat, where you get to see that force. You might not know that when you're younger, but we've introduced the concept of force at this point in your educational career. So the idea of a force is happening when there's 2 magnetic fields. So once we have the idea that 2 magnetic fields make a force, we're in good shape. Okay, so what ways could we make 2 magnetic fields? You could just get 2 magnets, 2 bar magnets, a north pole and a south pole, and you could find the repulsion or the attraction. Or you could take 2 sets of moving charges and see their interactions with each other. Or you can put a moving charge, inside of a magnetic field. And either one of these ways, you can get yourself a force. So the way that you're being introduced to this is the idea of a magnetic field. And we'll do it. So I'm not introducing the concept of in and out in my diagram. We'll look at it in a second. That way, but we have a magnetic field that's pointing, I don't know, let's say to the right. There's our magnetic field. And I have a proton gun, right? We're talking about the force on a positive charge that's moving. So I got myself a proton, pew, pew, and it shoots upward, or shoots towards the top of my whiteboard here. So I take my proton and I put it right here. It's positively charged, and it's moving in the upward direction with some velocity v. So when you're thinking about this, Tamba, you want to be aware that this charge that's moving inside of this magnetic field, this singular proton that's moving upward with a velocity, is generating its own magnetic field. And this magnetic field that's generated by this moving charge interacts with this magnetic field that's here, because we've got, I don't know, let's just say we have a north side of a magnet, and over here we have a south side of a magnet. So we have a magnetic field. You could think of a horseshoe magnet if you want. You could think of 2 different bar magnets. You could think of something that just generates a magnetic field. But that's where that red magnetic field is coming from. It's independent of what this charge is. But it interacts with the magnetic field that this charge is generating. And you can figure out the generation of that magnetic field by using this right-hand rule if you were concerned about it. But what we would want to do now is figure out, well, what direction is the force going to be on this charge because of it? So then we could say, well, they're perpendicular to each other. The angle between these two is 90 degrees, which is maximum. We could approach 0 if they're parallel to one another. But since they're perpendicular, we get a maximum amount of force. We would say that we found that would be Q, V, B, and they like to use that sine theta. In my class, the first thing I would describe is I want these to be perpendicular to one another. Okay, but they put that sine theta right there. And depending on your level of trigonometry, the sine of 90 degrees in degree mode on your calculator, the sine of 90 equals 1. So that's very valuable. Thank you, Tamba. So we've got the idea. As long as they're perpendicular, we got maximum amount of force. So what we want to do there is, I said it was a proton. Now, a proton has a fundamental charge, and that Q for one singular proton is equal to 1.6 times 10 to the negative 19. That's too small. My apologies. But I imagine what they would say is this charge right here has a certain amount of charge. I don't know. Do you have a number? Does it give you like a micro? Yeah, that's the trippy bar. Okay. So it gives you, does it give you something like this? These units right here, microcoulombs? Is that what it gives you? Haley, you're muted. Miss Spain, you're muted.
Okay, sometimes it gives you micro, and sometimes it gives you coulombs. You just have to be careful.
Okay, so
switches back and forth.
just like we've seen before with the idea of centimeters or kilometers or kilograms or something like that, all of these right here are metric prefixes, and they all stand for some shifting of the decimal, where centi means 100th, kilo means 1,000. So if I want to know how many grams, I need to take my number of kilograms and multiply by 1,000. So that's what we're going to do.
Hi, Melanie.
Hello, Melanie. We're working on right-hand rule, magnetic force on a moving charge. So with this micro, it's 1/1,000,000th of a coulomb. So micro is times 10 to the negative 6 whatevers. So you can have a micrometer or micrometer. Yeah. Melanie's here twice. So you just would substitute this value of micro with times 10 to the negative 6. How would that look if I were to write it down or type it into a calculator? Well, if I had 3 microcoulombs like that, basically this is a shorthand for scientific notation. This is just micro being some prefix. We would write it as 3 times 10 to the negative 6 coulombs. So when you see the micro, you just substitute the micro with times 10 to the negative 6. Now, on your calculator, depending on what you have, the most effective technique that I have is to just type it in as 3e minus 6. Excuse me, that's the wrong e. It should be the little capital E on your calculator.
So on the graphing calculators that we have at school, you just push
second comma. That would be what that would be. I'm trying to find a calculator here. So the calculator, I have a Casio here at the house. It just has a times 10 to the button. It's located right here. Okay. Yeah. Okay, so you have an 84. Perfect. Second comma. Perfect. Okay, so that's what you would do. You would just do 3 second comma minus 6, negative 6. And that would take care of your Q value. The velocity needs to be in meters per second, which I imagine they're probably giving you that velocity in meters per second. But your Q needs to be SI notation. It needs to be in coulombs. The velocity needs to be in meters per second, and the magnetic field needs to be in Tesla. That's the unit of magnetic field after Nikola Tesla, held back by Thomas Edison.
They had a few questions with Mila Tesla, but it's the
Okay,
same.
that's the same idea. So when you see milli, you just need to translate that to the lowercase m, not a capital M. That's the two different things. You do that as 10 to the negative 3. That's what milli would tell you, 1,000th. So do they just ask you to quantify, Tamba, the value of force? Is that what you're struck? Is that what we're trying to answer here? What's the value of the force, not necessarily the direction? Magnitude of the force, yeah. So just make sure you're in meters per second on your velocity, you're in Tesla on your magnetic field strength, and that the Q is in coulombs. And we talked about how you can take that micro and turn it in times 10 to the negative 6. And then I'll write all that stuff over here as well, so you can see all the unit breakdown. To get the force, you would use the right hand, the direction of the force. I just got to go through it because that's just the way my brain works. Your fingers represent the direction of the magnetic field. So we see that the magnetic field is pointing to the right. So I just rotate my fingers so they're pointing to the right. And then my thumb will tell me the direction of the moving charge. So in this case, the direction of the moving charge is towards the top of the page. So when I put my hand down, sorry, I have to reorient my body so I don't have to move too many things. I would set my hand down like this and see my thumb is pointing in the direction of the moving charge. My fingers are pointing in the direction of the magnetic field. And I find that the net force on this object would be into my paper. If you wanted to talk about the direction.
Coming from you, because it has to come from your palm, right?
Yes, the way I talk about it with my, yeah, that's what you do for Tom, that's what you do to get the force. I talk about it as if you were slapping somebody. You'd exert a force right here. You know, you don't get to do the back slap stuff. No back slapping. It's just, you know, you got to be, you know, a gentleman's duel or something stupid. Yeah, you just got to make sure you're in the correct decimal place and all of that. Micro stands for 1/1,000,000th, milli stands for 1,000th. There, so it's the generation of the magnetic field caused by the charge because it's moving that interacts with the magnetic field to make that force happen. Two magnetic fields potentially make a force. If they're parallel to one another, the amount of force is 0. And that's because it's all the angle. Right now our theta is 90 degrees. So we want the perpendicular part of it, right? So we'll draw a little picture here to make sure there's a little bit of clarification on that. But anything pointing to the right exerts no force. Those are parallel to one another. If I shot a proton from here to this direction, it would just move straight through the field. They wouldn't interact with it. That's because the magnetic fields would be interacting in a way that causes no net force. Uh-oh, my headphones just went out. So I'm going to hear you guys a little bit differently now, I think.
Working?
Yeah, I hear you a little bit differently now. Okay.
Okay.
But my microphone still works. If there's echo or anything like that, let me know. Let's say that the charge was actually shot this direction. You can see that there's a component pointing in the upward direction and a component of the palm goes into the paper. Yeah. If you see that this has an upward component and a rightward component, we would only concern ourselves with the upward component. Okay. Now, they do things weirdly, Tamba, and this is where some confusion could happen, because by putting sine theta here, your instinct is to always then put the sine of whatever angle they give you. But in the case of this problem, if I were to give you this angle theta right here, if I were to give you this angle that it was shot at, I would actually be concerning myself with the cosine component of it.
Mm-hmm.
So the more effective technique at the end of the day is to say that I want my velocity and my magnetic field to be perpendicular to each other. And you could always find that perpendicular component with sine theta. However, you might have to take this angle right here, do 90 minus that angle to find this angle right here. So there's a little bit more trigonometry that Edgenuity is doing with our students than we had done so far. But that would be where they're getting that sine theta from. I mean, if you look on the AP Physics 2 formula chart, they listed as a QVB sine theta. But on my AP Physics C formula chart, they do it a little bit differently. They do F equals QV cross B, where they introduce the idea that you want perpendicular components with the cross product as opposed to a dot product.
Mm.
Yeah. So you just want it to be perpendicular component to it. If they don't have a picture, I guess you have to make the assumption. Oh, Tamba put his hand up. I need to. Oh, no picture. Yeah, with no picture, you're just going to have to make the assumption. And if it doesn't get the correct answer with sine theta, you can just, if you get it wrong, then you just use cosine theta. Without a diagram, it's impossible to understand. So you're just guessing. But you do, if they give you an angle, it's either going to be the sine theta or the cosine theta, depending on which angle they give you. Not, I don't want to say always, Tamba. You know, always is a tough word to use. Anytime it's micro, it'll be times 10 to the negative 6. We do some problems. I do some problems in the AP class where sometimes that's milli, and that'd be times 10 to the negative 3. Sometimes we do pico, which is times 10 to the negative 12. But micro is this mu value. This stands for micro. Yes, and that means millionth, 1 millionth with a th at the end. So times 10 to the negative 6 is what this prefix represents. You'll find that in physics, we tend to only focus on multiplying or dividing by some number of thousands. So we go from typically base unit to kilograms to mega, or kilo to mega to giga, where we go 1,000, 1 million, 1 billion. And then we would go in the opposite direction. We do milli, micro, and then pico. No, not pico. There's one below there. It eludes me right now. My apologies. But then you'd go nano. That's it. Perfect. Thank you, Haley. Miss Spain. Yeah, you would do 1,000th, 1 millionth, 1 billionth, 1 trillionth is the approach. So at some point in your educational career, they focus on scientific notation, and then you take physics, and we don't care.
We spent a long time working on just like solving using it in chemistry.
Yeah, I find that ideally scientific notation is to make what you write easier, but the way it generally is presented, you're doing it as when in your practice, you don't understand its purpose.
Yeah.
Because you generally would only deal with things in an introductory class using the units that you'd want. But if you were always writing 3.2 times 10 to the negative 6 coulombs, it becomes a little bit more challenging in terms of nomenclature and writing a word problem or having that visibly listed. So this is technically written in scientific notation because it is 3 times 10 to the negative 6, where you only have that singular decimal place.
I never thought of it that way. I think that is more connected than the way I remember teaching it, because we we focused on the jump the decimal
Right. Yeah. See, and that's
method,
the
and
weird thing.
it didn't it didn't connect with, you either just had to memorize all the prefixes, or it didn't really connect with what you were doing,
Well,
you know?
I have like my main issue that I see, like Nathaniel, my son, will be working on. He'll be doing things where he has to write it in like hectometers or something, and I'm like, no
Well,
one uses hectometers. Like
it's
that's
just an
not
opportunity to
like that's just
convert,
a
right?
got 'em kind of question. That's
Mhm.
not a question that's applicable beyond like, okay, yeah, he's in sixth grade. Thank you for asking. But yeah, that's the like I'm like that's where I have to be not AP physics teacher dad and say like, teacher, don't, that doesn't matter. So that's usually the parent teacher conference that Yvonne, my wife, goes to, and I don't. So
Because perhaps she can find a more diplomatic way to say.
yeah, I'm just like, this is bad. I got into it with one of his math teachers in elementary school. Yeah, right hand rule is really something. You gotta tangibly do it. Like as someone who's taught it for a few years, I think about the only effective way to really do it is just to practice and have that immediate feedback of whether or not you got it correct.
Hmm.
So I like, well, I'll just draw a bunch of like the day that I introduced the right hand rules, whether it's this one, or the combination of both, is just by drawing lots of pictures and seeing the contortion of humans in my classroom aligning their hands appropriately with the diagram. Um, I still have students that will do it with their left hand
Hmm.
and stuff like that.
Yeah, like how do you know if you're holding it? I know maybe it would be better this, if you hold
I
it
have
this
no
way,
idea. Yeah.
or this way, you know?
Yeah.
You're
Yeah.
talking about into or out of the screen.
It's okay. So the first thing that I think is very, very difficult to think about is you're introducing a dimension that is typically not discussed. So we talk about up and down, the y dimension. We talk about left and right, the x dimension, but we rarely discuss the z dimension. So, I think about, like in my head, I play video games. Tomboy played video games for a really long time. So the idea of going into this is when you made the jump from playing Super Mario World, the greatest Super Mario game ever made, probably the best game ever made. Um, a 2D side scroller where you could jump up and down and you could move left and right, but you didn't have the ability to translate into or out of the page, and you couldn't go like this or that. Um, where when they introduced the just so you know, there's a reason why Nintendo named it the X and Y button. Um, there's the dimensions of X and Y. Um, so they introduced the Nintendo 64 back in the year 1996. I was a sophomore in high school, and they added a new button to the controller named the Z button. Well, why did they need? No, they added the Z button on the back end of that horribly designed controller, and the Z button was to indicate now you can travel into and out of the screen. Um, So if you can think about the X, Y, and Z buttons as being the approach of three-dimensional. Um, so you have to like you just think about the paradigm shift that video games went through when they went from being in a fixed to a 2D plane to now allowing the player to travel up, down, left, right, and in and out all simultaneously.
Hmm.
So if you think about that progression, that's the first thing you have to think about here is you can go, we have something going this way, up and down. We have something going this way, left and right. And we also have something going this way, sorry, and out. Here's a finger. So, um, that's the first thing. And that's the kind of conversation that you get to have. Miss Spain would have this wonderful conversation in her class with them. Miss Lagrona, we all know, would do that as well in her classroom.